Hi. So as an introduction, I would like to say that it's very humbling to speak just after the author of Message Pack, because almost 6 years ago, when I was living in Paris, I got a phone call from Solomon, one of the founders of a small startup called .cloud. I think nobody remembers .cloud, and that's totally okay. And basically, he was telling me, hey, do you want to come on our cool startup in San Francisco? And after a few months and a few trips to California, I said, yes, let's do that. And one of the first things that I started working on was on this cool kind of distributed RPC layer called Zero RPC, which is what happens if you take Message Pack and Zero MQ and you put them together. And that was one of our secret weapons at .cloud. The other secret weapon was Elixir and containers, and that generally people remember it better now because of Docker. But Message Pack was one of the things that we used, and if I remember well, that was more than 5 years ago, so my memory might be a little bit fuzzy, but I remember that we did some benchmarking with like Message Pack versus JSON versus some binary JSON stuff, and we kept Message Pack because it was super fast, the payload was small, it was super reliable, it worked in all the languages that we would try it on, so it was just like rock solid. And when you're building some startup-y thing, and so your code will often be not quite perfect, it's great to build that on top of code that works. So Message Pack was code like that. So if I extrapolate on FluentD, that means that you should totally use FluentD because it's solid. So yeah, that's what I wanted to say. So I'm Jérôme. I work for Docker. I joined Docker when it was not Docker yet, when it was .cloud. We were doing platform as a service, and we were using containers. And at some point in the end of 2012, early 2013, we decided to refactor our container engine and open source it. That became Docker, and very quickly everybody told us, okay, that .cloud pass thing, it's all nice, but stop doing that and just do only the container thing because that's way better and way more interesting. Among various things, like the last time I contributed something to the Docker engine, that was the privilege mode, because we wanted to have Docker in Docker, because that seemed a good idea at the time. And then later we realized it was maybe not such a great idea, so I wrote a blog post telling people, don't use Docker in Docker after all. So that probably makes me a rather confusing person. I do apologize for that. So now I have a few questions about you. Obviously, I can't really ask every single one of you what they do, but I just want to do a kind of show of hands to know who is using or plans to use containers soon. That almost everybody. Who is using or planning to use Docker? So that's almost everybody as well. Who is using or planning to use Compose? And that's less people, but still a lot. And all that stuff in production, either now or soon. And that's a lot of people. Great. If you answered no to some of those questions, I will pretend that you want to know about it anyway, because that's the only slides I have. Here, the general idea is that we're using Docker, we're using Compose, which is something to describe a complex application, a stack of containers. And maybe you're using microservices, maybe you don't, it doesn't really matter. What matters is that you have at least 2 containers, and even if you have a monorails, like a monolithic Rails application, you will have Rails and a database. So that's more than one, so you're in. And we have this working in our local machine, and now we want to go to production. We want to deploy in a cluster, we want to scale, and we want to take care of all the, the things that we don't think about when we are developers, but at some point when you go to production, suddenly it matters, like loggings and backups and what happens when a node goes down and all those things. So what we want to achieve is something like that. So I have here, I have a little swarm cluster, and I'm running an application using Compose on it. So if I do like Docker Compose PS, and maybe I should unzoom a little bit and hope that it's still readable. I have an application that is made of a bunch of containers. If I look at the Compost file, because if you've never seen a Compost file, I think it's worth explaining what it's all about. In this Compost file, I describe an application made of services, and so each service will be a container. So I have those two, RNG and Hasher, are microservices. Then Web UI is a Web UI. because I'm not very fancy when it comes to naming. Redis is a Redis data store, and Worker is a background worker. So that's my app, and for each component except Redis, I have a Docker file describing how to build it. For instance, for the worker, I have a Docker file for the worker saying, okay, use the Python image and do a couple of pip install and then execute that worker code. Then for the hasher thing, that one is based on Ruby, so I'm using a Ruby image and installing a few things, a few gems, and so on and so on. And since this is microservices style and everybody is free to use whatever they want and everything can mix and match, for the web UI we decided to use Node.js and go full microservices, which maybe is not a good idea to have like 3 different programming languages in the same project just like that from day one, but it's just for demo purposes. Now this application is running on my cluster, and I can go to the web UI I was talking about earlier using a conventional web browser. And this application is something I wrote for demo purposes almost 1 year ago when I started to do workshops about Docker and orchestration. And I wanted an application that would have all the usual suspects. I want a data store, I want a worker, I want web services, I want something that you can connect to with a web browser. So that's this application. It's a Docker coin miner, which is not at all like Bitcoin, except it has coin in the name. And we can scale it, and we will see that graph change when we scale. You can maybe see on the left here, we have numbers like 1, 2, 3, 4. That gives the speed of my app right now. And to scale, I'm going to use Docker Compose scale, and I'm going to say, okay, I want 10 workers. So when I do that, it's starting 9 more worker containers across my cluster. And by the way, if I use Docker PS to see the running containers on my cluster, I will be able to see them. I'm going to unzoom a lot because Docker PS is super wide. So this shows me all the containers on my cluster, and I have like 1 million containers. Well, I don't have 1 million containers. Only Google has 1 million containers, but I have lots of containers. And if we look in the last column where normally you have the name, and I'm going to unzoom a little bit more, so it's completely unreadable, but I will just like say what's going on. In the name column here, I will have like all those containers are the containers for my application. Those ones I will talk about later. And in front of each container name, I have like node 2, node 4, node 3, indicating on which node the container is running. So this shows me that my containers are really running all over the place. And I will try to prove it like this. Like you can see node 2, node 5, node 4. I have 5 nodes in this cluster. So there won't be node 6 because I'm not Google. I only have 5 nodes here. All right, so that's my application. I scaled, and if I go to this, I can see that, yep, my graph went up, so that's great, except if I can math, before I was at like 4 per second, so if I scale from 1 to 10, it should be at 40 per second, and I'm not at 40 per second, I am at 10 per second. This is because I have a bottleneck in my application. I have another service which is now like the choke point and is slowing everything down, and I will scale that service as well. So I'm going to do Docker Compose scale. It's RNG. I kind of cheat a little bit because I know what's going on, and so I know which service is slowing me down. So I'm going to scale that service, except that service is a little bit trickier. The first one is a worker, so it's just a process that connects to the rest of the application, but itself doesn't receive traffic. So I can just create many copies of it, and I'm great. But this is a web service. It's a tiny REST kind of web service. But if I create multiple copies, now I need to put a load balancer in front of it. And so here I see that my load increased. But behind the scenes, there was a load balancer that said, oh, you have more containers, so I'm going to add those containers to the load balancer so that they can all receive traffic. And to see that, now I'm going to go to, I'm going to talk about all those containers that we saw like before when I do that. Like all those containers above that line. Well, if you want to see that on the recording, maybe I should select that on screen. All those containers are containers for my application. And I have a bunch of containers here that make my logging stack. Then I have a bunch of containers making my local registry and a bunch of containers making console. So all those things are kind of core components of my platform. And so I have a logging stack. And if I want to be fancy, I can go to that logging front end and see what's going on. So this is Kibana, and I will explain more like how my logging stack works. And this is where I'm embarrassed because I don't remember exactly how Kibana works, but I'm looking for it's something like that. Yes. All right. And so somewhere in those log lines for my container, I should see the information I was telling about, like this. No, sorry, that I got the wrong one. It's that one. This is the thing that watches over my platform and says, oh, you have more backends in this service. So I'm dynamically reconfiguring a load balancer. And normally, how do I do that? Yeah, maybe I should learn to use Kibana someday. Right. See here, we can see what I was talking about. It says RNG-BE, which means backends for RNG, changed from that list of one element to that list of two elements. And just after, it says RNG-BE changed from that list of two elements to that list of 1, 2, 3, 4, 5 elements. So this is a container responsible for watching over my application and doing, oh, you have more backends? Fine, I'm going to reconfigure the load balancers. And then I have another container, which is the actual load balancer. So I decided to use a specific pattern, which is to kind of break down all the different roles in my stack and have a super fine-grained control on how load balancing works. In that case, I'm using HAProxy in simple TCP mode, but I could use Nginx, I could use HAProxy in HTTP mode, I could use active checking, passive checking, round robin, or list connection, or whatever kind of fancy load balancing I want. This is just one way to do things. It's not the best way or something, but it's a way I like because I'm the kind of person who loves to know exactly what I'm doing. So yeah, I have my application. It's up on a cluster. I can even shoot some nodes, not all of them at this point, but I can shoot some nodes and things will continue to work. And I have a central point for all the logs of my application, thanks to a stack that I will describe a little bit more in a few slides. So this is what I want to have. This is what I want to achieve. So now the question is, how do I get there? So I want load balancing, I want to scale, I want to deploy multiple nodes, I want to distribute container images, I want overlay networks, which is something so that my different containers can talk with each other easily. And for that, I will need a key value store. And I also need just to like provision my machines. How do I create those servers? In fact, somehow this is all upside down because really you will start with host provisioning and then we will put a key value store and then using the key value store have overlay networks and then add more and more features on top of each previous layer. So my outline will be first a little intro about best practices and pragmatism. Then I want to explain how I created that cluster. Then what is a key value store and why do I need one? What are overlay networks and why do we need them? How do we distribute container images? How do we deploy on Swarm? How do we scale? How do we load balance? How do we manage logs? And then I will, at the conclusion, explain that everything is changing super fast. So first, one of the ideas of Docker is batteries included but swappable, which means Docker is trying to come with everything you need, but if there is something you don't like, you're welcome to change it for something else. Like even the runtime itself, in Docker 1.11, we introduced something called containerd. So now instead of having the Docker engine directly starting containers, you have the Docker engine talking to containerd, and containerd is using runc, which is an OCI compliant backend. So between runc and containerd and OCI, I used many terms that maybe you're not familiar with. But what this means is that if you want to use another container runtime like Rocket, for instance, you can, because when Rocket will be compliant with the OCI runtime, then you can connect it to containerd, and then when Docker will start containers, it will use Rocket's runtime instead of Docker's default runtime. So we try to make every single component like removable and replaceable if it doesn't suit your needs. So we provide defaults for almost everything, but there will be at least one of the things in this stack that you will not like or that you will want to change, and that's totally okay. In some scenarios, you will have to make some decisions. Like, for instance, for the key value store, you will have to decide which key value store do I want? Do I even want a key value store? And some of those decisions are difficult. Some people like opinionated platforms that tell you, you should do this and there is no other way. And that way you just follow those instructions. We try to be opinionated in the sense that there are default values for pretty much everything, but you are welcome to change those values if you have different needs. So I'm going to be moderately opinionated instead of strongly opinionated, because I don't like when people tell me what to do. If I disagree, that's not great. So how did I provision this cluster? This cluster is a cluster of EC2 virtual machines, but the method that I'm going to show here is completely independent of the cloud provider that you will be using. There is a tool of the Docker ecosystem called Dhaka Machine, and Dhaka Machine provisions Docker machines, as the name implies, and it abstracts the differences between cloud providers. So you can do Docker Machine, create, using driver, Google Compute Engine, or using Amazon EC2, or using some OpenStack private cloud, or using DigitalOcean, or this or that. And that's all you need to tell it, and then it will take care of bringing up the machine. So if you are switching from one cloud provider to another, or to an internal private cloud, all you have to do is change that driver name, and Docker Machine takes care of everything. It will take care of generating TLS certificates and deploying those certificates to the nodes that you create, which is great, because if you have tried to do that manually, you know that it's extremely painful, unless you know the man page of OpenSSL on the top of your head. But generating certificates and deploying that to machines is one of the things that people found extremely annoying. It's necessary because we want security, but it's also extremely painful, and so a machine abstracts that for us as well. It also allows to integrate arbitrary resources using the generic driver. So the generic driver, this is, if you look at the workflow of Docker Machine, the way it works is that it creates a VM using a cloud API, whether it's Amazon's or Google's or whoever, and after that it will SSH on the machine, and it will finish the configuration. The generic driver just skips the first step. When you use the generic driver, you give to machine the IP address and the user to connect with, and it will SSH to the machine, and it will install Docker and configure Docker. So if you're not using the cloud, and you just like a traditional IT department, and they give you a bunch of machines, like this is your IP addresses and this is how you SSH onto those machines, it's super easy to take those resources and kind of put them in your Docker cluster with the generic driver. Docker Machine has some drawbacks, like out of the box, the credentials, like those certificates and everything, are stored on a single machine. So if you lose that machine, your credentials are gone. So you have to take care of that and save your credentials somewhere else. It also provisions only one machine at a time. So if you need to 1,000 nodes immediately, you will need to have some to do something about it, like either a big, super long shell loop or find some way. And it doesn't integrate extremely well with some specific constructs like auto-scaling groups on EC2. So that's also something that you need to work on if you need that. Some other options if you want to provision a bunch of Docker machines, you can use some manual provisioning. Like basically, you can go to like the EC2 or the Google Cloud control panel and say, I want a bunch of VMs, start those VMs. And then I think both support Cloud Init, which is this thing where you can provide a little user data. And in this user data, you just paste like this, like include https get docker.com, and when the machine boots, it will download that, execute it, and this will take care of installing Docker. So that's a nice way to transform any cloud image into a Docker-enabled cloud image. This is a big, scary command line to provision a Docker cluster with Swarm, with overlay networks, with replication on Swarm, with like all those things using the generic driver. Forget the upper part, which is like big and scary and has lots of dash weird options. Just look at this. If you replace this with the names, and you can just like the nickname and the IP address of your machines, and maybe like here you put like the SSH user, and then you run that, and it will take your machines, SSH into those machines, install Docker, and set up Docker so that the machines now form a Swarm cluster. And that's all you have to do. So that's pretty convenient. Now we need a key value store. So what is a key value store and why do we need one? We need a key value store for a bunch of things. For the Swarm cluster membership discovery, which is the mechanism so that the different nodes know about each other. That's the thing when I do like Docker PS, I'm talking to my Swarm manager, and my Swarm manager knows that in my cluster I have 5 nodes, and it will talk to those 5 nodes. How does my manager knows about those 5 nodes? Because the 5 nodes register themselves in the key value store. We also need the key value store for the overlay network mechanism. Overlay networks will give us a way for containers to talk to each other, a little bit like a multi-point VPN, if you will. And we also use that, for instance, for IP address allocation. Like when I start 2 containers at the same time in the same virtual network, I don't want those containers to have the same IP address, otherwise very bad things will happen. And so I need some kind of central thing to keep track of which IP addresses are in use. And that's also the role of the key value store. It's a little bit like a database, but we don't need like a full-blown SQL database. Key value is fine. And we stick to key value because key value is easier to make highly available than a complete SQL database. We also use the key value store for leader election. So when you have replication between the different Swarm managers, the way it works is that one is active and the others are just secondaries, like waiting to take over. And for that, it's using basic leader election. And instead of implementing its own leader election, it's relying on the key value store's leader election mechanism. And last but not least, having a key value store gives you a nice way to store the crown jewels, the super important things, like for instance the TLS certificates and the stuff that you really don't want to lose, otherwise you lose access to your cluster. You can put that in the key value store. So that's why we need a key value store. Here are a few of those key value stores. So first, I didn't put Redis in that list, and you could wonder why not Redis? Redis is super simple, it's super fast, it's a great key value store, we could use that, right? We could, but Redis is not highly available. Yes, you can do like replication with Redis and stuff like that, but it's not what we call highly available in that case. Highly available in that case means highly available and highly consistent, as in when I do a write to the key value store, I know that my write went to the key value store, and even if I lose like almost half of my nodes, everything will be fine, I won't lose data. Redis is not like that. If your Redis master node blows up before the data was replicated to the other nodes, your data is lost. And so that's not okay. So instead here we have key value stores like Zookeeper, etcd, Console, and those have strong consensus so that when you write something and the key value store tells you, yep, it's written, you know that it's written for good. And unless you lose like more than half of your nodes, you know that your data is safe. So which one do we want? So Zookeeper is great because it's super stable. It's been around forever. It's Java, which is good if you know how to operate JVMs, and bad otherwise. Then you have like newer options like etcd and console. The kind of the cliff between the two is that Zookeeper is older and more stable, and if you deploy Zookeeper, you will have problems, but you won't be the first one to have those problems. So if you look for the error message, and you will we will always eventually find somebody who had the problem before, and they generally have the solution. The downside of Zookeeper is that it's not extremely dynamic in the sense that if you need to add and remove nodes in your Zookeeper cluster, it's kind of a pain. etcd and console were both designed around the Raft protocol, and the Raft protocol had multiple design goals, but the two that I really like are that first, it wanted to be simpler than Zookeeper, like that the protocol used by Zookeeper, and also Paxos. So like one of the goals is like we want to make something simpler. Why? Because when something is complicated, it's complicated to operate, it's complicated to debug, and it's complicated to understand. If you want to feel, I would say, not smart, you can do what I did and try to read the paper on Paxos to understand how Paxos works. I tried, I think, 10 times, and then I gave up. And I felt really dumb. And then I tried to read the Raft paper, and I understood, I think, the second or third time, and I was like, yeah, this seems pretty reasonable and simple. And if somebody told me now you have to implement Raft, I'm like, okay, that's going to be hard, but I can do it. If somebody tells me you have to implement Paxos, I'm like, all right, I quit. So one of the design goals of etcd and console, or rather Raft, was to be simpler. Another design goal was this to be dynamic, and from the very beginning to allow nodes to be added and removed. Something about all those key value store, there is the notion of like primary nodes or server nodes that are really active in the consensus system, and then you have the other nodes. What this really means is that you get a smaller number of nodes to really like have the information and be part of the consensus. So when you query one of those nodes, it gives you the data, and all the other nodes are just kind of proxying or falling back to those central nodes. And without entering into too much details, well, the technical explanation is pretty simple. It's because when you do a write on one of those systems, you need to have at least half of the nodes acknowledging the write and telling you, I got it. So if you have 5 nodes, you just need 3 OK writes to continue. If you have 1,000 nodes, now you need 501 nodes to tell you, I got it, before you can continue. So the more nodes you have, the slower it gets. So you don't want to have too many nodes. So generally we have like 3, 5, 7, 9 of those nodes, and everybody else is just like connecting to those nodes instead. So that's one thing. So which store am I using in this demo? I'm using console. Why? Because I just found it like really easy to deploy for that specific use case for that kind of demo. Like some of you will probably use etcd or Zookeeper. Like typically, if you are a big Java shop and you have a whole army of people who really understand the JVM really well, you probably want to use Zookeeper because the knowledge that you have of Java and the JVM will be extremely useful when operating Zookeeper, for instance. But on the other side, if you like hate Java and don't want to touch it with a 10-foot pole, then you probably want to use etcd or console instead. Here I decided to do something kind of weird. If we look at this output that you can't read, I'm sorry, but I'm going to explain like one little part here. Like the last 5 lines here are console containers. So my Docker cluster is using console, and console is running in containers. But those containers are in Docker, so basically Docker needs console, but console runs in Docker. So how does that work? It works because when you start your cluster, you're telling Docker, like that was in the super big scary command line, like here. I'm telling in the configuration, I want to use console for swarm discovery and also for overlay networks. And when I do that, Docker will try to talk to console, it will try to connect to console. But if console is not available, instead of crashing immediately and stopping, it will say, that's okay. I can't do clustering, I can't do overlay networks yet, but I'm going to try again later, and maybe that will work. And in the meantime, if you're asking me to do anything related to networks or clustering, I will tell you, nope, the key value store is not available, so I can't do that. But if you're just trying to run like normal local containers, that will be fine. So what we do is that we start the cluster, and the cluster is not fully functional because the key value store is not available. But then we can start the key value store on every node, and at this point, the cluster becomes fully functional. So this is another slightly less scary, but still scary command line that I use to start console. I'm using the official console image, which was released, when was that, like a couple of months ago. The only really interesting thing to note here is that when you start those console containers, you have to tell them how many console nodes there will be total, so that they can know when they have consensus. Because remember, when you want to write something in console or etcd or zookeeper, you need to have a majority of the nodes to be there before you can tell, yes, we've wrote that thing. So in the beginning, when the nodes show up, they don't know how many nodes total there will be. So when there are like 5 nodes, they're like, oh, are we like 5 nodes among like a total of 5, and then it's okay, we can go? Or we are 5 nodes, but they're going to be 11 nodes total, so we don't have the majority yet, and we should wait. So to kind of solve that, when you start console, you're telling console, this is how many nodes we need before we can continue. Now, overlay networks. So overlay networks, that's this kind of, it's like a little bit like VLAN if you've done networking, like with the real network, the one with cables and stuff, not the Wi-Fi thing that never works. Then VLANs is a way to have a kind of private network over a normal network. And I think almost nobody does VLAN anymore, at least in the cloud world. Like if you go on EC2, you can't do VLANs. No, instead you have like VPCs, which is a little bit like VLANs, but not exactly the same thing. In particular, you don't have broadcast, you don't have multicast. So the overlay networks are a way to have a private network for a bunch of containers. Like my application is running on a private network. My logging cluster is on a different private network. All my components, all my different applications on my Docker cluster will be each on a private network. Under the hood, it's using something called VXLAN, which is totally different from VLAN. VLAN is Ethernet on Ethernet. VXLAN is Ethernet on UDP. And since it's on UDP, it works everywhere, including in the cloud. And it needs a key value store to keep track of which container is where. So basically what happens is that when you create a container on one of those overlay networks, Docker will be like, oh, I need an IP address for this container. So it will look in the key value store, what's the next available IP address in this network? All right, that's 172.18.0.4. I'm going to assign that to container ID FF3 something something something. And then at a later point, if there is another container trying to send the packet to 172.18.0. I don't remember which number I said, then that Docker node will say, okay, what is this IP address? I'm going to look up in the key value store, say, okay, it's container ID FF something something, which is located on this node, so I'm going to route this packet to the right node. So that's how it works. And you can use overlay networks directly with the Docker CLI. It will look like something like this. You can say, okay, let's create one of those networks, like my app, and then I can put a bunch of containers, like database, and then 3 web frontends, like web 1, web 2, web 3. And an interesting bit is that I can start those 3 frontends and give them a network alias, and I can give them the same network alias, which means that now when I'm in this network and I'm trying to resolve the name www, it will give me the 3 IP addresses of those 3 containers. So it gives me a really simple way to discover backends. That's how my load balancer configuration system works. It's kind of constantly resolving the name RNG well, RNGBE, like RNG backend. And each time that the set of IP addresses changes, it's like, oh, something happens, I need to reconfigure the load balancer. So you could do that, but there is like Compose integration, which is a little bit easier to use, where you can define your networks. You can say I have a public network, a private network, and then you can decide like the www service will be on the private network, and then I'm going to have a load balancer that is simultaneously on the public network and the private network, and you can give different network aliases, and so on and so on and so on. Forget everything you know about software-defined networking. Now you have YAML-defined networking, which is way better, I think. All right, the next step is we need to distribute our container images. So why do we need to distribute images? In our Compost file, we have something like this. Like we say the www service is built using a Docker file in the www directory. When I want to go on a cluster, this kind of doesn't really work anymore, because if I build my container image, it will be built on one node of the cluster. And now if I want to scale, the other nodes are like, I don't know what image you're talking about, because you only built on this node of the cluster. So what I need to do is to build my container image, and then I need to store it somewhere so that all the other nodes can pull it from that place. So in that case, the easiest option is to use a Docker registry. So it's Docker registry is just a library for Docker images, and there are tons of options. Like we could use the Docker Hub, we could use like the commercial thing like Docker Trusted Registry and Docker Data Center. That costs you some money, which I know we don't like to pay money, but at some point this is what pays my salary. So if some of you could get licenses for Docker Data Center, that would be awesome. And we also have an open source thing. So basically, if you do docker run registry:2, this will download like the public image of the registry server and run it on your cluster, and you get like a free Docker registry for your cluster. The difference between like the commercial thing and the open source thing is that in the open source thing, you just get like the raw image hosting thing. And in the commercial version, you get like a super nice web front end and permissions and teams and automated builds and this and that and whatever. So here, I decided to use my own local registry. And if I go back to the completely impossible to read screen, this bunch of containers, I'm going to highlight them. And in fact, should I try to zoom that a little bit? Yes. Let's be crazy and let's look here. I have a bunch of containers here, and so one is the actual registry. So I have one container, which is the registry that has my container images. And then I have little reverse proxies running on every single node. And on each node, there is this little reverse proxy that listens on port 5000 and forwards traffic to the actual registry. The reason for that is that I can go on any node of my cluster, and on any node I can talk to localhost port 5000, and when I do that, this will forward the connection to the registry. Maybe the registry is on node 1, maybe it's on node 2, maybe it's on node 3, I don't know. I'm just talking to localhost port 5000, and it sends me to the registry. The reason why I do that is because the Docker engine wants you to use TLS. You have to use TLS when you talk to your registry. But I didn't want to like set up a TLS certificate and obtain like an actual certificate, or even I could use Let's Encrypt or something like that. But I didn't want to go through all those steps. So I used the fact that the Docker engine insists on using TLS except if the registry is on localhost. If the registry is on localhost, then the Docker engine is fine with you not using TLS, because the Docker engine thinks that when you connect over localhost, even the NSA can't really snoop your communication. So here, this hack allows me to not use TLS, not set up certificates, and use the local registry basically. All right. This is the Compost file I use to set up that registry. So I have my front-end service, which is the little proxy bit, and the back-end service. So at this point, we have a cluster of Docker Engine nodes that can run containers. I can manage all those containers and all those nodes with a single API endpoint with Swarm. Like when I do Docker PS, I see the containers on my whole cluster. When I do Docker info, I see the information of my whole cluster with memory usage and everything. I have overlay networks so that I can create private networks for my application. And I have a self-hosted registry so that I can distribute images for my application. What do I need now? I need to actually deploy my application on my cluster, scale, load balance, and logging. So I'm going to use Docker Compose, and with Docker Compose, by default, if I do Docker Compose up, this will build my container images, and it will start them, but it will start them only on the nodes where the image was built. Remember, at this point, I don't have I'm not using the registry yet. So if I build my images and just start them, they will only start on some specific nodes. So what I need to do is to adapt my Compost file so that instead of using the build keyword, I'm using an image keyword. And I'm going to show a little before-after thing because I think that's the easiest way to understand what's going on. That's the before Compost file where I have build this service here, build this service, build this service. And the after file is that one. And so after, now the image, so for each service, instead of having build using this directory, it says run using the image taken from my local registry. So what I do is that before running my application, I build it, then I tag the resulting images and I push them to my registry, and then I create a new Compost file which tells exactly which images I should use. Yeah, I have a better before-after thing here. So you can see every build section is replaced with use this specific image on the registry. All right. So when you deploy on Swarm, you get this mechanism when you do a Docker run. Instead of starting on one node, it will pick one specific node. It will do some scheduling to decide on which node the container should run. And so when you use Docker Compose scale, under the hood, Docker Compose scale just does Docker run, Docker run, Docker run multiple times until it has the right number of containers. So each time it does Docker run, Docker run, Docker run, Swarm will pick a new node to put that container. So all your containers end up being spread on the cluster. If you want to debug what's going on, you can still use Docker logs, Docker exec, Docker inspect, Docker stats, like all the normal Docker commands. There is some implicit co-scheduling, which means that if you're using some advanced features like volumes from and --net container, automatically those containers will be put together. So for instance, if you know the concept of pods in Kubernetes, when you have a bunch of containers sharing some resources, you can automatically have that. If you say this is a container and now this is a bunch of other containers that use the same volumes and the same network, then they automatically get placed together on the same node. So how do we scale services? So here I'm going to do a kind of more generic comparison on what it means to scale different kind of services. So there is the obvious, scaling stateless services is easy. Scaling stateful services like databases is hard, but it's more subtle than that. First, you have stateless workers. So workers are services that don't accept connections from outside. They are the ones connecting to the rest of the infrastructure. Maybe it's just like a cron job running every hour or every minute or every day or whatever. Maybe they are pulling some jobs from a task queue. So those things are the easiest to scale because you just create more copies and that's it. You don't need load balancers, you don't need anything fancy. You just create more copies and that's it. Then we have stateless services. So those ones accept network traffic, and then that's when things get more complicated because you need a way to load balance those network requests across all the instances. However, if they are really completely stateless, it means that each request could be handled by a new container. Like if you are really completely crazy, you could do something like, oh, I have a web request, I have an HTTP request, I'm starting a container just for this request, dealing with the request, sending the response, and then I'm destroying the container and putting a new container. It sounds a little bit crazy, but if you take a few steps back, there are systems working like that. Maybe you've heard like recently all the deal about like serverless infrastructures. So I'm going to make a kind of little comparison. When I started like sysadmin stuff in the late 90s, I was doing serverless. I was not like a pioneer or super in advance or something. Everybody was doing serverless because everybody was doing mutual PHP shared hosting. And that's serverless. I mean, you write a little function, it's a little bit of PHP code, and then you send that to the server, and then there is a URL, you can call that URL, it executes the code. If that's not serverless, then I don't know what is serverless. So, and if you look at how the PHP environment works, it's not creating a container, of course, but it has a small environment, and each time you have a request, it is initialized, it does a bunch of things, and then normally everything is destroyed, and then the next request shows up, and so on and so on and so on. So this idea of starting a little something, processing the request, and then it goes away, that's kind of what PHP was doing in the late 90s. So now if we talk about real containers and with like strong isolation guarantees and not just like the PHP environment, this also exists. There is a crazy project by, I think, Russians called Erlang on Xen, which is exactly what it sounds like. It's Erlang, the programming language, but instead of running on Linux or Windows or whatever, it runs straight on Xen, the hypervisor. So it's like instead of booting Linux, you boot Erlang, and it boots super fast. I don't remember the exact numbers, but it's like maybe 10 milliseconds or something like that. So it means that if your web app is written in Erlang, then you can like boot it for each HTTP request. You boot the VM, and the VM serves the request, and then it goes away, and the cost is only, say, 10 milliseconds. With 10 milliseconds, on the one hand, it's a lot. It's very long, 10 milliseconds. On the other, if you think that it gives you perfect isolation, because this is a VM, so nothing comes in, nothing comes out, it's really strict, then it's not so bad. So this idea of spinning up environments and then making them go away works great for stateless services. But sometimes you have services that have some ephemeral or local state. For instance, let's imagine you have something like Facebook or Twitter with an activity feed, and so each time the person like connects to see their feed, it's getting data from some backends and something, and this takes a while. So the first time they connect, it's kind of slow, but then if they connect again, if you can send them to the same server, the server can keep things in memory and serve the response immediately, and maybe just like update the last post or something. So here, your system is stateless. Like if the server goes away and you put another server, that's fine, it will still work. But you can gain performance if you can have like some affinity between the client and the server. So you can still scale very easily something like that. But it's great if you can ensure the affinity using something called, for instance, you can have session cookies, which is like when the first time the client connects, you set a cookie, and the cookie basically indicates which backend should serve the query, so that later when the client connects again, you look at the cookie and you say, okay, last time you were here, the backend was this backend, so I'm going to send you to the same backend because this backend has all your data in cache and the request will be way faster. So that's a point, and that's a perfect example of a scenario where you want to have some fine-tuning on your load balancer. You don't want just like some round-robin thing, sending connections randomly or even on the least loaded backend. You want something that lets you route precisely this client to this backend. Or maybe you want to look at the client ID and do some hashing so that this slice of the user ID space is mapped to a specific backend each time with consistent hashing. So this is the example showing how to do that with Swarm, and this is a kind of that's YAML-defined networking, and that's kind of a hack. I'm going to try to explain what's going on here. In my stack, I have a www service, and all my code is connecting to www. So when I'm running in dev, I just have my www service, and I'm connecting to that, and all is great. Now I want to put a load balancer, but I still want to connect to www. So what I do is that I put the load balancer in the default network. I put the www service in a separate network, and in the default network, I give the alias www to my load balancer. So now, when in my default network, if I try to connect to www, I connect to the load balancer, and the load balancer sends my traffic to one or multiple www backends. All right. Harder and harder, data stores with, so stateful services. Okay, but there are different kinds of stateful services. The ones with built-in symmetric replication, like console, etcd, RIAC, so those are kind of great because you don't have to worry about who's the primary, who's the replica, what's going on. You just connect to one of them and it works, because then it will kind of route the connection internally and everything will be fine. So this is relatively easy to deploy in containers. Then asymmetric replication is when you have, like most SQL servers, you have a primary server and then you have replicas, and you have to connect to the primary, because if you connect to the replica, at best it will tell you, nope, I won't accept your write, and at worst it will accept your write, but it will become desynchronized, and that's terrible. So you need some kind of extra layer, some extra smart thing here to make sure you connect to the right server. And this becomes like harder to put in containers. To see an example of this pattern, like you can see a Patroni from Zalando. It's an open source kind of a little framework and set of tools so that you can run Postgres with replication in containers and automate the whole like replica provisioning, failover, and so on and so on. And then you have data stores with no native replication at all. Like this is a data store and it doesn't have any kind of primary, secondary replica or whatever. And so the old school method is to buy some extremely expensive hardware, like a SAN that has like replication to another SAN, and you use that. The other option now is to use some container storage system. And I have a bunch of names here that you can look up after, like Flocker, Portworx, BlockBridge, and those will take a bunch of machines and create some block storage with that and expose that to your containers. It's a little bit like Gluster or Ceph, if you're familiar with those technologies, but those have been designed specifically for containers. And often, I mean, a little anecdote is that I was contacted by Portworx to say, hey, do you want to test our stuff? And I was like, yeah, sure, why not? That could be fun. And the first round of testing, I was like, okay, that sounds extremely interesting, but with containers, I became an extremely lazy person. I just want to git clone the repo and do Docker compose up, and I hope that everything will work. With your thing, I have to compile a kernel module and do this and that. I'm too lazy, I can't. And I say, okay, fine, good point. How can we automate that? And so we had a little bit discussion about that, and long story short, now you just have to clone a repo and do compose up and the thing works. And if you compare that to the amount of work that is required to get Ceph to work with Rados and the Rados block gateway and everything, that's night and day. That being said, stateful services are hard to operate. And the question you should ask before being like, oh, I'm going to put MySQL and Postgres and RIAC and Cassandra into containers, the first question should be, first, is it really my job to do that? My job, not like me as the sysadmin, but is the value add of my company that we are running a data store? Do I really want to run my database myself, or can I just like outsource this? Because by increasing level of difficulty, it's always easier to get someone else to do it for you. That's kind of obvious, but there are many companies. If you don't have a huge Postgres, you should probably just use like Heroku Postgres or the Amazon Postgres thing or some other provider, and not worry about your Postgres thing, because those people operate like thousands, I wouldn't say millions, but thousands for sure, of Postgres clusters. So they know what they're doing, and you can now like concentrate on your actual value add. It's slightly harder to run your data store in containers when you know containers. It's slightly harder to run the data store outside of containers, but what is certain, like for sure, is that if you don't know containers and you try to run your data store in it, you're going to have big problems. So don't like, if the first thing you must run in containers is a database, please stop because you're going to run into problems. Start with the kind of easy things like a web front end, some API backend, and then once you start to have some experience with that, then you can think about, okay, now we can move databases in containers. I want to talk about logging, and so here, initially my demo was using ELK, Elasticsearch Logstash Kibana, and then I noticed that we would be here, and so it felt inappropriate to have a demo using Logstash. So in the Caltrain on the way here, I switched the demo to use Fluentd, and that worked. And I'm going to show a little bit what this logging stack looks like. So it's in a different window here. So that's the, I don't know if EFK is an actual thing. It's Elasticsearch Fluentd Kibana. I just replaced the L with F, but I don't know if that's how people call it. So how does that work? So I have a Compost file, and in this Compost file, we have Elasticsearch. So Elasticsearch is a JSON document store. So you can throw JSON stuff at Elasticsearch, and it will store them and index them. Those JSON documents here are log lines. Each log line is a little document with like which host is this from, which container is it, what's the log line, what's the timestamp, what's the container name, what's this, that, whatever. Each log line is a little document, and everything is in this Elasticsearch cluster, so that I can do requests like get me all the documents or log lines for container XYZ. Then I have Kibana because I'm not very good at making raw Elasticsearch requests, so having a Kibana frontend is nicer. It's just like a web frontend that will talk to Kibana and expose the logs. And I don't know how to use it very well, but I use it better than raw Elasticsearch for sure. And then we have Fluentd. So Fluentd, in that case, is receiving the log entries from the Docker engine, and it's sending them to Elasticsearch for storage. And I didn't do something too fancy here, so I'm going to show the config file, and probably people are going to throw rocks at me because my config file is totally not best practice, but this is Caltrain quality code. Let's see. So I have a little Docker file here when I say, okay, I'm going to install Fluentd, and I'm going to install the Elasticsearch Fluent plugin. And then I'm going to put a config file in my container. And then I'm starting Fluentd. And my config file, that's the most embarrassing part, I think. So I'm just like accepting logs on port 24224. That's the default port. So this is accepting like ports using, I think, the Fluentd protocol. And then I'm sending everything using the Elasticsearch plugin to my Elasticsearch cluster. And here, Logstash format is not really Logstash format, it's really like Kibana format. It's so that Kibana can see, oh, that you have those logs in your cluster, so I'm going to display them. And flush interval is the only thing that I had to hack a little bit, because by default, one of the strengths of Fluentd is that it will buffer the messages. And so for demo, it's not so great because you have to wait for a little bit until Fluentd like flushes the buffers. So I changed that from 1 minute to 1 second, which is not great for production, as I was told, but for demos that works. An actual config file would be more complicated than that. Like typically, you would want to make sure that the logs coming from different containers will be tagged differently and maybe sent differently. But here I wanted to have a really generic thing that you can like put that in your cluster, and boom, you get all the logs sent to a single place. So we do that. Then we use Docker Compose. Let's see, almost. Yep. And so with Docker Compose, I asked Compose to make sure I had like one Elasticsearch container, one Kibana container, and 5 Fluentd container So I have one fluentd forwarder on each of my nodes. That's I think that's the architecture that I showed earlier. It's like we have this fluentd thing sitting on each node. The only thing I don't have is a central aggregator because Caltrain. But in a real setup, we would have this extra aggregator and deal with failover that way. And then, last but not least, if we look back to my application here, in the Compost file, at each container here, I've added a little extra logging section saying to Docker, instead of writing the logs locally in JSON file, I want you to use the fluentd driver and send logs to localhost 24224. And that's it. So overall, when I'm building and deploying my app, I'm not making like manual changes in this file. What I do is that I start with that file, which is much nicer and cleaner and simple. And then what I do is that I have multiple scripts. I have this script that will, okay, fine. So this script will build my app, and then it will push the app to the local registry, which here was super fast because the Docker caching system kicked in, and so it only pushed the missing layers. And now it generated a new Compost file. So at this point, this Compost file only has this. So each build section has been replaced with image, 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 and so on and so on. And like, okay, now I need load balancing. So I have another script to automatically add load balancing for me. So I want a load balancer for the RNG service. So now in my file, instead of just having like RNG is using this image, now I also have RNG on its own network. I have the load balancer for RNG, and the WD is watch DNS, so the thing to detect when I add backends and dynamically set up the load balancer. And last but not least, I have another script which is add logging. And when I run that, it just patches this to add the fluentd options in my Compost file. So the technique is I have my nice, like easy to edit, readable Compost file, and I have a number of pipeline steps to transform that Compost file into what I'm going to use in production. I personally like this approach a lot because this is the final thing. I'm not supposed to edit it manually, but if something goes wrong, or if I want to really like figure out what's going on, and this is still a Compost file. I can still use Compose, I can still edit that, I can still read it, even it's a little bit less readable because there is more stuff, but I can still understand it fairly easily. So this is how I deal with logging. And so the result is this interface here, and you probably want to do some stuff like this, and should be like yeah, one day I will learn how to use Kibana correctly, but today is not that day. Yeah, container name, and normally here I should have message. Yeah, anyway. All right. So that's the files I use for my cluster. I don't know if EFK is really like the term people use. All right. So what about high availability? Like what happens if I lose a node? Swarm itself has pretty good redundancy. It has like this leader election mechanism. So if like one Swarm manager goes away, another Swarm manager will step up and let me control the cluster. Containers rescheduling is a different story. Container rescheduling is what happens like if one node is down and unavailable, the containers on that node need to be restarted somewhere else. And this is something that we're working on extremely actively. We just released a few days ago something called SwarmKit, which is a kind of new way to deal with that. And now we are seeing how to use that to manage clusters. what I want to highlight is that things in the Docker ecosystem move super fast. This is a kind of timeline, like over the last 6 months. In Engine 1.9, we added overlay networks, and they worked kind of okay, but there were lots of kind of rough edges, and lots of people were like, oh, those overlay networks, But a few months later, in February, we added some extra features in overlay networks, and they started to be really solid. When I was in February, I was in Paris giving a workshop on all those things, and I was demoing like rescheduling. So I was like rebooting a node and let's see what happens, and it didn't work really well. And I was kind of embarrassed about my demo, and somebody told me, well, don't worry. I remember like when you released overlay networks, it didn't work very well either, but now we're like 2 months later and overlay networks work super well. So today, like the demo that you're making with like shooting machines and seeing what happens, it doesn't work super well, but I'm not worried because I know that you're working on this and in a few months it will be way better. The 1.12 release, which is due any day now, I think we made the RC1, the release candidate, yesterday or something like that, is going to give a lot of improvements and lots of new things with high availability and rescheduling. One thing is that the Docker ecosystem in general, and that's true for all the things in the container space, like Docker, but also Kubernetes and a lot of other things in that space, move really fast. So sometimes when you see that something doesn't work quite well, instead of being, oh yeah, maybe in 2 years it will work, it's more like, no, in 2 months this will work and this will be solid. And it's not only Docker, it's just like containers in general. Those things move super fast now. And also the last thing is that next week there will be DockerCon, so as you can guess there will be lots of announcements and things and everything, so lots of things will also change after that. That's pretty much all I got. If you want to know more, all the examples that I gave here come from a workshop that I delivered almost like twice a month for the first half of the year in Europe and in the US. This workshop is entirely publicly available, like the slides, the scripts, the demo app, like everything is in a public Git repo, so you can use it, abuse it, you can do whatever you want with that. And that's pretty much all I got. Maybe we have time for questions or not, I don't know. Thank you.